Hi, good morning students. Today I am going to present second PUC chapter number 2, Boolean algebra. In this chapter we are going to discuss some problem solving techniques, as usual some algebraic methods to solve the problems. So before going to introduction, let us discuss about this chapter weightage. According to NCERT or syllabus, this chapter is for actually 9 marks. From this chapter we will get 2 marks questions and 1 5 marks question, totally the 9 marks chapter. So from this chapter one compulsory 1 5 marks question will come. That must be in a very easy to solve the problems like a K-map or some De Morgan's theorems. Let us discuss later that. So now directly we will move to the introduction of this Boolean algebra. So in this chapter we are going to discuss some problem solving techniques. So you may get one questions in your mind, why this chapter name is called as Boolean algebra. So according to this particular chapter, we should tell one great mathematician, that is George Boole. He introduces some techniques to solve the problems. So in the year 1815 to 1864, hence he will be the father of symbolic logic, and also he is the father of Boolean algebra. Dear students, one thing you should remember, in this chapter we are going to discuss some binary numbers like zeros and 1, and also this algebra deals with true and false. Some statements are true and some other statements are false. These kinds of algebra is also known as a switching algebra, hence Boolean algebra is also called as switching algebra. And in this chapter, algebra deals with the binary number, zeros and ones, as we discussed earlier. Some zero, we are always treating that number to represent a false statement. And also 1, it should be represent always true conditions. So hence 0 and 1 will be implementing these numbers in this particular chapter. So, and also this will be a very clear to solve the problems, because here we will get some charts and also tables. So this must be enough to introduction. And if we directly move to the particular concept of this chapter, binary valued quantities. So in this binary valued quantities, variables and constants. If you are able to see on screen some words, see here also some statements will come. What is a truth values, and what are all a false statement and what are all true statements, and what is a truth table. So according to this particular concept, now we are going to discuss these 2 important definitions. A sentence which can be determined to be true or false are called as logical statements. Once again I will repeat, a sentence which can be determined to be true or false are called as logical statements. Before just we discussed, the false statements are always represented by 0 and the true statements are represented by 1. That should be a particular 2 definitions, logical statements. And also the variable which can store the truth values are called as logical variables, are also called as binary valued variables. These can be stored one of the 2 values, 0 and 1. The decisions which results into either yes or no. Yes, we are treating as a true statement, or also binary number 1, and no, that should be a false statement, are also represented by 0. Is called as binary decisions. We know that decision should be a right or wrong. We have the two particular choices. So here also for the statement we have the two choices, that is one must be a true or false. These kinds of the particular values are what we called as a binary decision values or binary decision. So after this we will come to a very important concept in this chapter, that is a truth table. So previously you may not heard this word truth table. It is actually one type of the table. So here with this table we will discuss some how to represent the variables with inputs zeros and 1. So particular, a truth table is a mathematical table used in a logic to computer functional values of a logical expressions, or we will call simply like this, which is a table which includes both possible inputs and also it produces some single output, a table or a column. So this is what we call as truth table. A truth table, another one definition we will call like this. A truth table is a table whose columns are statements and whose rows are possible scenarios. So we will describe some this with one example. Consider one example. See, here the two variables are there. The variables are A and B, and also in this table we are considering some operation, that is logical AND operation. Usually we will call that is a AND means that is multiplication operation. So in this table, if you are observing this table, see here the variables A and B, if you are observing these two variables, that is A and B, and the result is y is equals to A into B, multiplication. So binary values, that must be maximum possibilities for the two binary numbers 0 and 1. We will write a maximum 4 combinations, that is 0 0, 0 1, 1 0 and 1 1. So according to the multiplication rule, the first in two inputs 0 and 0, 0 into 0 means 0, 0 into 1 again 0, 1 into 0 0, and both two binary inputs 1 and 1, 1 into 1, that must be 1. So this is the brief description how the truth table will works. Just we are explain the inputs and what the outputs we will get in this particular table. So in the above truth table, see, if the result of any logical statement or expression is always true or always a 1, that is called as tautology, and if any results, almost all the possible outputs in the truth table, a false or 0, are also called as fallacy. They may ask the question for the 2 marks, a question like this: define tautology and fallacy. This particular concept is related for truth table, in which truth table the whole result is true. True means 1. That is what we called as tautology. And sometimes in a truth table almost all results will get the 0 or false statements. These kinds of particular statements are what we called as a fallacy. Tautology and a fallacy, very very important definitions, remember. After the tautology and fallacy, we will come to the logical operations. So based on these logical operations, next chapter in logical gates we will discuss very deeply. But in this chapter, just briefly we are explaining what is a logical operators and how these operators will perform and what are all the manipulations on these particular logical operations and how these operations will work. And if we are applying any operations based on the problems and how this will be a react. So this is the concept, logical operations. So next concept in this particular chapter, that is logical operators. See, there are three logical operators that are not, or, and. Not gate, or gate, and gate. We will call like this. And also these three gates are also called as basic gates. These operators now used in a computer construction known as switching circuits. This also may ask one question, definitions, or sometimes in Viva also. What is switching circuits? If any circuit contains these basic operations, these logical operations, this is what we called as switching circuits. So now we will go to one by one logical operations and how these operations will work. Okay, see, in that logical operator, first operator, that is not operator, and also we will call the not operator like complementary operator, or also complementation, negation, or also that is also called as a inverse gate. Inverter also. What is the another name for not gate? That is inverter. So by all these names we will call the not operator. Now we will directly come to the not operator, how it will be work. So the not operator is a unary operator. The operator operates on a single variable. This is a key point for this particular definition. Of course, a not operator will also accept the input, but it should be a single input and also produce single output. This is the major characteristics compared to the and or gate with the not gate. And or gate will accept more than two inputs, two and more than two inputs, but not gate, not like that. Not gate will accept only single input and also single output. So this is what we called as not gate. The operation performed by not gate operator is called as complementation. So according to this, we will call operator not, what the operation that must be called means that is a complementation or negation. And also we have one symbolic representation for the not gate. That is the symbol we are using for the not gate, that is bar. Excuse me. That is bar. If any variable having a bar, that understood, that is a not gate, that is complementation. So in below example, we are able to show one example. So if x is an a having a value 1, if the not gate will implement to that particular value, automatically the value will becomes its inverse value, that should be a 0. Because we are using the two binary values 1 and 0. For the complement of 1, the result is 0. For the complement of 0, the result is 1. So we are showing in that example. If you are observing the screen, I am marking. So if the x is equals to 0, then the complemented result of the x is 1. So this is what we called as not gate, and we have some truth table for the not gate also, and we have particular symbolic representation, but in next chapter we are going to discuss how to write the not gate symbol. Okay, but now we will go for the truth table for the not gate. So in this particular truth table, as we said the definition, always not gate accept a single input. If you are going to observe one input, that is x, and maximum possibilities for this input is 2, that is 1 and 0. Check the result side. X is an input and complement of x, that should be a result. So that is what we called as representation of x with x bar. So now I will show that result also. See, this is the part what we will discuss now. If any variable in a not gate, that is complement, it will be converted into complemented value. So that we will call for the x is x bar as a result. And also check the result. If 1 is an input, result is 0, and vice versa. This 0 is an input and 1 will be the output. So this is the truth table, what we are calling as NOT gate. Another name of the NOT gate is inverter gate, remember students. And also NOT gate is very important to switching circuits where we need the inverse operations. If you are having a knowledge about inverters, in our home we are having the UPS, inverter, UPS and all these things. We are using NOT gate for these operations. When the power is off, on that particular time, UPS will get a power automatically on. How that UPS will coming to know now the power is off? Again, there the technology is we are using. In first chapter we discussed about this in UPSs. That will a inverter will helps to for the UPS to on. That's why that is the conversions of the powers, that is off condition and on condition, like that the UPS will work like that. That is also called as inverter technology. So let us conclude about that NOT gate, and directly we will go for the second particular logical operation, that is OR operation. So in this OR operation, before going to the definition of the OR operation, OR means, that is here we are calling simple mathematically, that is addition. OR operator is a binary operator, operates on the two variables. So observe this a particular point, dear students, because previously we discussed the NOT gate. There that will be accepting a single input and producing single output. But if I come to the OR gate, this is a unique queue. It will accept not only two inputs, more than two inputs also it will be accept and produce single output. So this is what we called as OR operator. And the operations, particular simple arithmetical operations for logical OR is addition, remember. And the symbol we are using for the addition, as you know, that is a plus symbol we are using. Hence in this particular operator we are using a plus as a sign to represent the OR operation. So this is what we called as logical addition. Logical addition. The symbol we are using, of course, a plus. We will discuss about some example to explain this OR operation. Consider the two inputs x and y, and the result is x plus y. Of course, x and y are the two inputs and the result is x plus y. The two inputs 0 and 0, 0 and 1, 1 and 0 and 1 and 1. Apply the logical addition rule, that's all. 0 plus 0, that is 0. 0 plus 1, that is, I am showing now, 0 plus 0, that is 0. 0 plus 1, 1. 0, 1 plus 0, that is also 1, and also 1 plus 1, according to the binary addition rule, we will write that is also like 1. Remember students, in this particular truth table, only one possible input we will get the result as 0, that is when both inputs becomes 0 or low. We will call and by another names for the inputs. Sometimes for the 0 we will call as an off statement. Sometimes for the 0 we will call for the low statement. Sometimes for the 0 we will call also called as false statement. So by different names we will call the binary numbers, but the operation is same. And also remember the truth table. Addition, whenever two inputs are 0, that time only we will get the possible result is 0. Rest of all other cases, any one input will becomes high or also means 1, hence the result is also 1. So this is what we called as a brief description for the OR operation. After this we will go for the third logical operator, that is logical AND operator. So similarities between OR and AND are very not much, but operation is different. Because why we are discussing about this point means, except NOT gate, whatever the logical gates we will get here onwards, almost all gates will accept 2 or more than 2 inputs. So in that, this is also a one list, that is AND operator. So if I come to the definitions for the AND operation, this operator is a binary operator. This operator operates 2 variables and produce a single result. And this operation performed by AND gate is also called as logical multiplication. Remember students, for OR gate, previous OR gate, that is logical addition, but for the particular AND operation, that is a logical multiplication. And you know the symbol of the multiplication. Usually we will use the cross sign, but in our particular computer language, we are, instead of cross language, we are using, that is a dot. The symbol we are used to represent the logical multiplication is dot, and we will describe through one best example, that is x again and y are the 2 inputs, and what will be the maximum possible result. Consider 2 inputs x and y, and the result is x into y. So maximum 4 combinations of the inputs, again 0 0, 0 1, 1 0 and 1 1. Check the results. Apply the logical multiplication rule for these inputs. Dear students, one thing you remember, either addition or multiplication, you should follow binary addition or binary multiplication rule. So in this particular truth table, 0 into 0, of course 0. Any input out of x and y, any one input is 0, 100% the result is also 0. That is a basic mathematical rule, you know that. But in this truth table, when both inputs are 1, on that time only the result is 1. So 1 into 1, the result is 1. Rest of all other cases, the result is 0. So this is what we called as AND operator. These 3 logical operators are also called as, we discussed earlier, that is basic gates. Basic gates. So by using these gates only, now whatever the operations we will conclude to solve the problems. So this is a brief description about the logical AND operator. After this, we are going to a next very important concept, that is in particular Boolean algebra, that is Boolean postulates. So if you are seeing on screen, that is Boolean postulates. So now directly will come for the Boolean postulates, are also called as Boolean theorems. Postulates or theorems, properties, theorems, sorry. So the fundamental laws of Boolean algebra are also called as postulates of Boolean algebra. Fundamental laws or fundamental theorems are also called as postulates of Boolean algebra. So if you are seeing the second particular point, the postulates for the Boolean algebra is originate from 3 basic logic functions, AND, OR and NOT. What we earlier discussed about 3 logical operations, AND, OR and NOT, based on these 3 functions only, whatever now we will discuss the properties of zeros and 1, that will be belongs. So directly I will come for the first basic postulate, that is a properties of 0 and 1. See, observe this particular postulate or a property. If x is not equal to 0, if x is not equal to 0, then x is equals to 1. If x is not equal to 1, then x is equals to 0. I think you are getting, this will be a particularly what we are calling that is properties of zeros and 1. If x is not equal to 0, then that might be a complemented, that must be a 1. If x is not equal to 1, that must be another complemented result, that must be a 0. So this is what first a particular property. And if you come to the second property, it should be also called as OR relation or logical addition. We discussed earlier, logical OR is also called as logical addition. So in that first, as we discussed the truth table, the same results also, here also we will write that is a properties of zeros and 1. 0 plus 0, that is 0. B, 0 plus 1, that is 1. 1 plus 0, that is 1. And 1 plus 1, that is 1. In this particular property, when any one input is 1, the result is 1. And the last condition, that must be both possible inputs are 0, that time only we will get the result, that is 0. These are all the maximum 4 possibilities for the zeros and 1 for the OR relation or logical addition relation. Then next one, that is AND relation, and also called as logical multiplication. Same rule, but here we will, for the 4 maximum combinations, 0 into 0, that is 0. 0 into 1, that must be 0. 1 into 0, 0, and 1 into 1, that is 1. In this particular truth table or a property, if any one input is 0, 100% the result table is also 0. When both inputs are 1, that time the result is only 1. Rest of other cases is 0. This is what we called as a third property. And fourth one, that is complement rule, and also called as complement rule, we are using with the help of that is NOT gate. Whenever both inputs 0 and 1, with complemented result is vice versa. If it is a 0 complement, the result is 1. If it is 1 as a particular input, that will be a 0 will be the complemented result. Dear student, just observe on the screen. Now I will show how represents a particular symbolic representation for the NOT gate. If you are observing, see, this is a particular NOT gate representation. So if it is X is an input and X bar will be the output. If 0 will be the input, 1 will be the output. If 1 will be the input and 0 will be the output. Whatever the input you give for this particular NOT gate, that should be complement its value. That's why this gate is also called as inverter gate. So this is about complement rules. So now we are going to the next concept of next properties, that is principle of duality theorem or principle of duality. So in this particular theorem, this is a very important theorem to solve some complex problems in this particular chapter. This is very important principle used Boolean algebra. It states the definition, the statement of the principle of duality states. Sometimes, dear students, remember in annual examination they asked this question, state principle of duality for the 2 marks. Of course, in Boolean algebra we will get the 2 marks question. So in that, sometimes they asked this question, state principle of duality, give an example like that. So very important definition, remember. This particular statement states 3 particular operations, that is statements. See, changing each OR sign to an AND sign. OR sign means that is plus, to AND sign means that is dot. That is the first particular statement. Second one, changing each AND sign to its OR sign. AND sign means again dot, dot into plus. And third particular statement, replacing each 0 by 1 and each 1 by 0. So these 3 are the major important statements in principle of duality. Once again, I will tell like this. The first statement, changing plus with dot. The second statement, changing dot with plus, and third statement changing 1 with 0 or 0 with 1. This is the statement for the principle of duality. Wherever you will get the operation, just change with its definitions or statement. Now we will explain with considering one example. Find the duals for the following Boolean expression, and sometimes for 2 marks they will give the 2 examples of Boolean expression and write its dual form. That also one possible question from this particular concept. So remember, students. So in that the first example, that is x plus 0 is equals to x is a Boolean expression. Dear students, I am showing the first statement, x plus 0 is equals to x. So in this particular expression, you just identify out of above 3 statement which statement will suit. So if you are observing x plus 0 is equals to x, in Boolean expression you are identifying a logical operation, that is plus. Plus means or sign. Now you have to change the or sign with and sign. Or sign with and sign means plus sign is converted into just a dot sign, and check the result statement dual form. See, x and operation plus is converted into x plus 0 is equals to x. That should be converted expression is x dot 1 is equals to x. Here the conversion expression is plus is converted into dot and 0 is converted into, that is 1. So in Boolean expression, left side expression what we are getting is equals to x, and right side dual form expression is equals to x is the same, because that is a variable. We will not apply for the variable for the principle of duality theorem. Just we are applying only for the logical operations plus, into and binary values zeros and 1, not for the variables. So this is the first Boolean expression. Consider second one. So here same, x plus 1 is equals to 1. As we see a previous truth table, we are using that is OR operation. So here we are identifying that is the OR operation plus is converted into and, that is dot, and 1 is converted into, that is binary value, that is 0. So apply that rule, x into 0 is equals to 0. The second expression. So this is what now I am showing. So in this particular expression, Boolean expression, plus is converting into dot, 1 is converting into 0. If you are observing right side expression, it's a dual form, and right side expression is equals to 1. Here in dual form, x into 0, that is 0. Very simple expression, simply a simple expression. And also if you are coming to the third particular Boolean expression, that is here 2 variables are there. X into x is equals to 0. They are given one binary value, that is x into x is equals to 0. Now if I want to write its dual form, means just you change the 2 operators, that is dot is converted into plus and 0 is converted into 1. X into x is equals to 0, third Boolean expression, that is converted into its dual form, that is x plus x is equals to 1. Remember the duality forms, because we are using these particular dual forms to solve next some other problems, to solve that problems, because we will get some complex situations. On that time we will utilize these particular expressions, remember. And coming to the fourth expression, in that particular fourth expression, x into y plus z So here also, if it is Boolean expression, now convert this Boolean expression into its duality form, just converting, that is plus with dot and dot with plus. So its a dual expression is x plus y into z, x plus y into z, that is the fourth expression. And final Boolean expression, that is like this: x plus x into y is equals to x plus y is a Boolean expression. Now we have a chance to convert this Boolean expression into its duality form. Consider here x and plus x into y is equals to x plus y. Apply where the plus is there, you just apply the dot. In between x and y, where I am telling about the Boolean expression, left side expression. Here the left side expression is x into y, x plus x into y. In the right side expression, that will be converted into x plus y. And check the results. Is equals to x plus y, is equals to x plus y. But when you are coming to the duality form, that is x plus y will be converted into x into y. So this is what we called as a principle of duality theorem, and describes by using these examples. Not only these examples, we will get so many examples. So this is just a description how the principle of duality works. Then after this principle of duality, now we will go for important concept in this chapter. Again, the next theorem we will call, that is as a next theorem, Boolean theorems. So some series of theorems we will get. So before going to explain these theorems, previously we discussed now the properties of zeros and one. So same properties they here mentioned by list wise: 0 plus x is equals to x, 1 plus x is equals to 1, 0 into x is equals to 0, 1 into x is equals to x. And second particular theorem we are discussing about that, later we will state, and how to prove this idempotence law we will discuss. But this law states, this law describes x plus x is equals to x and x into x is equals to x. Both properties we are going to discuss. That's one's for addition and one's for multiplication. And after that we are going to the next particular theorem, that is a complementary law. In previous classes you may heard the word complementary law. X plus, this law states x plus x bar is equals to 1 and x into x bar is equals to 0. Complementary law. This is usually very important law to solve the De Morgan's theorem, I think. So remember this theorem. For the addition rule, whenever x plus x bar is equals to 1 and x into x bar is equals to 0. Then the next theorem, involution law. X bar is equals x, double bar is equals to x. If any variable complement twice, we will get the same variables. That's the definition of the involution law. Then after this involution's law, that is commutative law. That is commutative law. So this also you may heard the word in the previous classes. So this law states x plus y is equals to y plus x for the addition, x into y is equals to y into x multiplication. After this theorem, we will discuss about associative law. X into y z is equals to x into y z, and this is for multiplication, and some for the addition rule, x plus y into z is equals to x plus y into z. Then distributive law, x into y plus z is equals to x into y plus x into z. X plus yz is equals to x plus y into x plus z. This is also distributive law. And some absorptions laws list mentions they given, and one by one we will discuss about that. The x plus x into y is equals to x, then x into x plus y is equals to x. Next one, x into y plus x into y, that is equals to x. X plus y into x plus y, that is also x. And x plus x into y, that is equals to x plus y, and final expression, that is x into x plus y is equals to x into y. So these are all the basic theorems. We are going to discuss how to prove these theorems with the help of some different methods. Okay, so now let us consider the first best method to solve any theorems, that is what we called as perfect induction method. You may get one question, what is perfect induction method? See dear students, you are using whenever you are solving a problems in algebra, let us some considering ones for the variable 0 and some other we are considering the let x equals 0, let x equals 1, like that you are considering the values. This theorem, this method is also explained the same technique. So before going to the perfect induction method, let us see what is the definition. It states, okay, Boolean theorem can be provided by substituting all possible values of the variable 0 and 1 in this technique. Proving the theorem is called as perfect induction theorem, or also simply we will call like this. Perfect induction theorem means considering for any variable all possible values like 0 and 1 to solve the problem. This method is what we called as a perfect induction method. So in that particular first theorem is in our list. So as we discussed earlier in that particular table list, this is the first theorem. 0 plus x is equals to x. Dear students, now I will show the proof of this theorem by using perfect induction method. See, as the statement say, the perfect induction states, sometimes we will consider the variable x is equals to 0 and x is equals to 1. Observe on the screen, you are getting some LHS expression. Now we have to prove that into RHS, left hand side and right hand side expressions. So now I am considering for that particular expression 0 plus x is equals to x, let x is equals to 0, or if x is equals to 0, just apply wherever the x value is there, just you apply 0. So hence this expression is converted into x is converted into 0. So that is hence this operation we are doing. 0 plus 0, that is equals to 0. So 0 plus 0 is equals to 0. LHS is equals to RHS. So consider, but perfect induction method says all possible values, means not only for 0. Again we have to solve the same theorem with considering let x is equals to 1. Same theorem, just apply if x is equals to 1, what will be the expression? See, in the right side expression, so that is equals to 1. 0 plus, if you are observing, I am showing that expressions. 0 plus x, that should be an LHS expression. Now I am applying where x is there, instead of x I am applying that is 1. So then 0 plus 1, according to logical addition rule, 0 plus 1 is equals to 1. So hence that must be 0 plus 1 is equals to 1. LHS is equals to RHS. So this is the perfect induction method. Students, you remember maximum students, because we have an experience for the valuations, and that time we are observing maximum of the students, whenever they are solving the problem by perfect induction method, they are considering only one value, that is x is equals to 0 or x is equals to 1. That is not correct. you should consider both the values, once for x is equals to 0 and once for x is equals to 1. You have to show by these two values. So that is what we called as a perfect induction method. For the same theorem, 0 plus x is equals to x, we have a chance to show by different method. That method is what we called as by truth table method. Same, if you are observing that a particular right side, one particular table, here we are showing same theorem I am writing as an input, 0 and x are the inputs, and expression is 0 plus x, that must be is equals to x. So now we will consider sometimes x equals 0 and sometimes x is equals to 1 with the help of the truth table. So check the second row. Now I am given the value for x. Observe this column. Value for x, sometimes if it is 0, then the expression, LHS expression is also 0. Sometimes for the x value, now I am given that is 1, that expression is also 1. That is 0 plus 0 is equals to 0, 0 plus 1 is equals to 1. So like that, we will solve the theorems by using perfect induction method as well as truth table method. So now let us come to the second theorem. Second theorem, that theorem says 1 plus x is equals to 1. 1 plus x is equals to 1. So again you just apply the perfect induction method. So here let x is equals to 0. Then LHS is 1 plus x. Instead of x you apply 0. 1 plus 0 means that is 1. That should be equals to RHS. Again now you consider the same particular theorem, but now here that is whenever the let x is equals to 1, then what will be the LHS expression? 1 plus 1 is equals to 1. According to binary addition, 1 plus 1 is equals to 1. Hence here also right side expression is equal to left side expression. Hence this theorem will be proved by perfect induction method. Now we have one more method, that is truth table method. So in this particular truth table method, same what we are discussed earlier, the expression we will write in the truth table. 1, I am showing 1 plus x, 1 and x are the two particular inputs, and expression is 1 plus x. Sometimes for the x I am considering 0, and sometimes for considering y, x is also 1. Then 1 plus 0 is 1 and 1 plus 1 is also 1. Hence this theorem is proved with the help of truth table. Dear students, these theorems are very important to solve the next major problems like some De Morgan's, or also some you need to solve some K-map. On that method these points of the inputs will help to solve. Then coming to the third theorem, that is multiplication rule, logical multiplication. 0 into x is equals to 0. Same method. Perfect induction method, now you consider x is equals to 0. What will be the LHS expression? Apply wherever x is there, just 0. 0 into 0 is equals to 0. Then once again you consider for the x value that is equals to 1. Then LHS is 0 into 1 is equals to 0. As we know the binary multiplication rule, any input multiplied with 0, 100% we will get the result is also 0. Then coming to the truth table method for the theorem 3. So in the truth table, same expression, 0 and x are the two inputs, and 0 into x will be the expression. So once you apply for x is equals to 0 and x is equals to 1, if you are observing the right side expression, if you are observing the expression, both the result of this particular theorem is also 0. So we have a chance to call this type of results previously we discussed when all the possible results of a truth table will becomes false or zero. That statements are also called as fallacy. So because here both inputs are zero, this is what we called as fallacy. Remember students. Then after this we will go for the next theorem number 4, that is what we called as, this is also multiplication rule, that is 1 into x is equals to x. 1 into x is equals to x. Consider 1, that is x is equals to 0 in the LHS expression. Wherever x is there, apply 0. Right side expression is also will becomes the 0 because 1 into 0 is equals to 0. Consider once again in the right side expression x is equals to 1. In that particular LHS expression, wherever x is there, consider with 1. 1 into 1 is equals to, the result is 1. Here two different possible results will get. For once you consider 0, the result is 0. Once you consider for x, the result is 1. Let us check by the truth table method. See, in this particular truth table, 1 and x are the maximum possible inputs and 1 into x will be the expression. If you are considering for x is equals to 0, then result is also 0, and for x is equals to 1, the result is 1, because in binary multiplication 1 into 1 is equals to 1, 0 into 1 is equals to 0. So because in this a particular truth table, if you are observing the input, they are given the wrong input, that must be 1. 1 into 1 is equals to 1. In this particular document, the input is 0. That's wrong. When both expressions, when that must be 1. 1 into 1 is equals to 1. So this is what we called as some properties of zeros and 1. Dear students, up to now we are discussed some particular logical operations, truth tables, and operations of how that AND or NOT gate will work, and some properties of zeros and 1, how to solve the properties of zeros and 1 with the help of induction method as well as truth table method. So up to now we discussed very important concept for the Boolean algebra. In the next class we are going to discuss some other important theorems are there. If you are observing the screen, again I will come to that list of the theorems. See, this is the list of the theorems. So in that now we discussed these 4 theorems. So after this, in the next class we will going to discuss some other rest of the theorems, that is idempotence law, complementary law, involutions law, and commutative law, associative, and absorptions and distributive laws. Thank you dear students, and be practice by writing these expressions on your rough or notebook. Practice to solve this theorem. Pause this video. You will get the expressions on screen. Write that expressions on your notebook and try to solve by own. Once you see the video, and after that you practice that particular theorems to solve, because sometimes they may ask this question, theorems, to prove the theorems also for the 2 marks. Thank you dear students. We will catch you in the next class.